Alright, so this is lecture 16 on calculational techniques for the shape operator. I'm just going to begin with the definitions for E, F, and G, the so-called warping functions. So these account for, in some sense, how the partial velocities are, changing from point to point. This is the length squared of xu, the length squared of xv, the partial velocities, right? And the f here has to do with the, well, of course, the length of xu and xv, but also the angle between them. One very nice case, excuse me, is given to us when f is equal to 0. If f is equal to 0, then we have what's called an orthogonal patch, right? Oh man, there's another name for it. Oh, anyway, we'll get back to that eventually. So moving along here, if you have two vectors v and w, we can write them in terms of xu and xv because xu and xv are linearly independent. They form a basis for the tangent space. And so if you work it out, like you do here, you can see that the dot product of two vectors in the tangent space is completely based on, of course, the components of the vectors, but more, the weights are given by the e, the f, and the g. This has to do with the other, also, by the way, the other popular approach to calculating geometry of surfaces, the so-called first and second and perhaps third fundamental forms. We'll get back to those eventually, but again, we're following O'Neill here for the most part for now. But of course, there's a connection between this, the e, the f, the g, and also the formula for the unit normal, right? Because the unit normal, you take xu cross xv for the patch, you normalize it, right? Divide by its length. And so xu cross xv, the length of this, well, that's given by Lagrange's identity, one aspect of it at least. The dot product of xu with xu times xv with xv, the length squareds, right? And then minus the dot product of xu and xv. So by these definitions we just gave, that's e, g, and f squared, so eg minus f squared is the length squared of xu cross xv. So this is the formula for the unit normal has to do with this division by this factor. I think, although I don't have my book right with me at the moment, but I think this is, he calls this w. It's either, I think that's what's called w. So like, you could write u is equal to xu cross xv divided by w if you. And I think use of that w actually does simplify formulas considerably, but I have not invested much effort into seeing that carefully. So I'll move along here. So next we look at accelerations of the partial velocities. Basically, accelerations of the coordinate curves. So UU, UV, VV all mean the thing you'd expect them to mean, where the patch has x, y, and z component functions. Now, given these, then we define the L, M, and N, which are the shape operator in the u or xv directions, dotted with xu or xv, and then M is xu dotted with xv, like that, which of course is equal to this, because the shape operator is symmetric, as we proved last time. So then, given this E, F, G, and L, M, N, you can go back to last lecture, right, where we proved on page 17 these, ignore this, oh, sorry, ignore this. We proved these lovely formulas for the Gaussian curvature and the mean curvature in terms of the determinants of these shape operator, right? So if you take these formulas and you replace v and w with x sub u and x sub v, right? So like this would be xu dot xu, xv dot xv, xu dot xv. In other words, this would be e, that would be g, f, and f. So you get eg minus f squared from this determinant, right? And same thing down here. You get eg minus f squared from that determinant. That would be L, this would be M, this would be, I think, N, no, M again, as in mommy, and this would be N as in nanu nanu. Anyway, so in view of this identity and the definitions we just made, out pops these formulas. All right, so lovely, lovely, lovely formulas. Nice, convenient formulas to use to actually calculate Gaussian curvature and mean curvature. I mean, it gives you a specific path, right? You calculate these derivatives, you take these dot products, you put them together like so, there you have it. Gaussian curvature, mean curvature, right? So that's nice. Nice formulas, at least. Nothing else. So, moving along here again, this lecture is primarily about, you know, how do you, some nice formulas for calculating these things that we talked about more geometrically last time. So here's a lemma. L, M, and N are also given by the unit normal dot, you know, XUU, XUV, XVV for M and N respectively. So the L, M, and N have to do with the accelerations of the patch along the coordinate curves, right, dotted with the unit normal. So they're measuring something about how the unit normal compares to the accelerations. Although I guess is that an acceleration? Well, I don't know. It's something. Anyway, these are nice formulas, of course, for L, M, and N. Again, U is the unit normal. So, excuse me. So the proof of this basically follows the argument we gave back in lecture 15. It really follows from the curve definition of the covariant derivative and product rule. We went through the calculation last time where we proved the symmetric property of the shape operator. Maybe you remember that. So let's get to it. Some examples. So I mostly follow O'Neill here because his examples are good and they're not you know, too much trouble to follow. So here they are. So the helicoid is basically a helix connected to its axis, like it's, well, if you can understand what this means, but he has a nice picture in the book. You should look at it. I have not attempted to draw it here. But anyway, so there's the patch for the helicoid, and if you calculate the partial velocities, you get this and this. Cosine V sine V0 minus U sine V U cosine VB. And then the accelerations are 0, this lovely thing and that lovely thing. So you can calculate E as XU dot XU, which is cosine squared plus sine squared, which is 1. This XU dot XV, the partial velocity dot product, you get minus cosine sine times U plus cosine sine times U plus 0. Hey, well, that's 0. So F is 0 here. And then G is xv dot xv, which gives me u squared sine squared plus u squared cosine squared plus b squared. So, of course, sine squared plus cosine squared is 1. So we get u squared plus b squared for G. You can calculate the, you know, the unit normal as being 1 over the square root of u squared plus b squared. Uh-oh. Oh, yeah. Sorry, I was looking for EG minus F squared, and I couldn't see it for a second, but EG is U squared plus B squared, F squared is 0, so that is EG minus F squared, as I was hoping for. Or the W. Sorry, I said I wasn't going to talk about it. Nah, can't stop. Alright, anyway, so B sine V minus B cosine V U from the cross product of this and that. Of course, I always like to check the dot product of this with that gives me cosine sine minus sine cosine plus 0. Hey, that's 0, that's good. And then for the xv dot this, I get ub sine squared minus ub cosine squared, so that gives me a minus ub, and then I get a plus ub from the z components dot product. So yeah, u is perpendicular to the partial velocities as it ought to be. And so once I have u, then I can calculate the L, the M, and the N. L being 0 because XUU 0 M works out to minus B over W. And N is 0 because the unit normal is perpendicular to the XVV in this case. So, okay, take all that. All right, remember it. And, oops, showing my formulas. So we've just calculated L is 0, M is this, N is that, 1, 0, B, G. And so we substitute those into the alphabet soup formulas, as I like to call them. Because, I mean, honestly, folks, I mean, they're lovely formulas and all, but where's the, I mean, it's just a formula, right? I mean, formulas are nice, fine. But, you know, definitions and geometry and linear algebra is better. So, but I guess at some point or another you want to calculate something, right? So here it is. So the Gaussian curvature Ln minus m squared over Eg minus f squared. And so you get minus b squared over b squared plus u squared squared. And there you go. That's the Gaussian curvature of the helicoid. Now, u being 0 takes you to the axis of the helicoid. I mean, it's the z-axis. Excuse me. And there, I think, is where the, let's see here, you get like minus b squared over b to the fourth. So you get 1 over b squared, where u is equal to 0. And then as u goes to infinity, this becomes very, very large. And so the curvature goes to 0, so it kind of like flattens out as you get further and further away from the z-axis. So that's kind of cool. Think about that. I don't have a good sense of what mean curvature means yet geometrically, I'll be honest. But here it is, it's 0, which means that the helicoid is an example of a minimal surface, all right? Okay. You can also calculate the principal curvatures, because last time we learned that the principal curvatures were the mean curvature plus or minus the square root of h squared minus k. So the k1 and k2 have to then be plus or minus b over b squared plus u squared. All right. And O'Neill also gives us some hints on how you can calculate principal vectors from all this stuff, but I haven't quite, well, personally, I haven't completely understood that bit just yet. There's many homeworks in this section which are very fun. I've only worked through a certain subset of them at the moment. Oh well, time is short. Here's another example. So the cylinder, r cosine u, r sine u v. Now we calculated Gaussian curvature, mean curvature for this through sort of more geometric, quasi-rigorous arguments. I would call them partly geometric. Now I'm just going to calculate it straight from the patch and these formulas. Here it is. So there's the partial velocity, which makes my e r squared. And then I calculate the v, which is just 0, 0, 1. So this and the partial velocities are perpendicular, so that makes f equal to 0. G, length squared of xv is 1. You can calculate the accelerations, bam, bam, bam. So 2 of them are 0. xuu is just that again, which I recognize as minus the radial vector. It's like, you know, if we think about this being the cylinder, xuu is just the one that's pointing inwards, right? It's like, oh, I can't. So then, of course, L, oh, I also need the unit normal, right? The unit normal, I always forget to calculate that. The unit normal is cosine u, sine u. So that's like this. Oop. Just pointing out if this is the z-axis, and then, you know, the radial vector points out. All right, anyway. So you take the dot product of this and that, this and that, this and, well, these two are easy, 0 and 0. This dot product that gives me minus r cosine squared minus r sine squared, which gives me minus r for L. And then put it together. So again, the Gaussian curvature Ln minus m squared over Eg minus f squared, also known as w squared. Oh, sorry, I said it. So this gives me curvature being 0. As we remember, the cylinder is flat, all right? And the mean curvature, on the other hand, is minus 1 over 2r. Both of these we calculated by different techniques in a previous lecture. All right. Then the other example which O'Neill gives, and it's a lovely example, the saddle surface. Really nice example, actually. I mean, it's complicated and yet simple. There's a lot to it here. So I'm following example 2, which is on page 229 to 230 of O'Neill. The Monge patch, XUV, UV, UV. So there's our kind of standard thing. Calculate the partial velocities, bam, bam, right? This one's interesting. E is 1 plus v squared. F ends up being UV, the dot product of that, and that's UV. The length of XV, the G, is 1 plus u squared, right? You take the cross product of these two guys and normalize, you get this animal, the unit normal. It's easy to check that this and that and this and that, that the unit normal is in fact perpendicular to the partial velocities. It must be. Otherwise, you calculated the cross product wrong more than likely anything else. At least that's what my Calculus 3 students always do, and you know, a lot of what we're doing right now is Calculus 3. All right, fine. And so you then calculate the accelerations, right? The UU, the VV, both 0. XUV ends up being 0, 0, 1, otherwise known as U3. Anyway, so there's your L, your M, and your N. 0, 0. The M is interesting, though. It's 1 over the square root of that. Lovely stuff. So you can calculate the W squared, or EG minus F squared, and you get, when you multiply this out, you get 1 plus U squared plus V squared plus U squared V squared minus U squared V squared. So the U squared V squared terms cancel, and it just leaves you with 1 plus U squared plus V squared, like that. And so this allows us to calculate the Gaussian curvature. Again, using our alphabet soup formula, it works out to this lovely beast. Oh no, look at that. For shame, for shame, for shame. I forgot my... There we go, all better. Because after all, there's 2 of those factors in there. All right. And of course, you can also calculate the mean curvature, and it works out to this lovely mess, minus uv over the square root of 1 plus u squared plus v squared to the 3/2 power. And since u is x and v is y, essentially, all right, geometrically, and z is u times v, I can rewrite these in terms of x, y, z's if I want. And as you can see, I have been consistent in my mistake. There we go. All better. All better. All right. So there you go. And I may have inadvertently at some point or another thought that the mean curvature for the saddle surface would be 0. You know, and I can't remember if that's something I'm remembering or something I actually said. I shouldn't have said it, obviously, if I did, because it's not always 0. It happens to be 0 when z is equal to 0, which is that one point we investigated at the start of all this, right? That one point, the origin, the mean curvature is 0, but pretty much everywhere else, except when z is 0. So z is 0, like along the, you know, the x and y axes, right? Which are special curves for the saddle surface, right? Those are, let's see, x, and let me think about this for a second here. X, so z equal to 0. Well, I can't see anything from here. All right, well, anyway. So there you have it. Let me stop thinking. Thinking is dangerous, I shouldn't do that. All right, so moving along here to page 7, I foolishly tried to do some homework. I will tell you that numbers 8, 9, and 10 of section 5.4 look interesting, and I don't know, I've spent some time on 9, and I can't get it to work just yet. I believe 10 should be simple enough to work through. I should have got 9. I'm bothered I haven't gotten 9 just now. I've spent a little time on it, I couldn't get it. Maybe you guys can get it. But this one's low-hanging fruit, and it's worthwhile. Patch x is orthogonal if f is 0. Show that s is equal to this, and s of xv is equal to that, all right? This is just a simple exercise in what is it, you know, you have an orthogonal basis for a vector space. Well, then all you got to do is you take the dot product, right? And that gives you, it would give you, if xu had length 1, this would give you the projection of the shape operator in the xu direction onto the xu direction. Except the thing is, xu doesn't have to have length 1, so I have to divide by that to be fair. So dividing by this is giving me a length squared, so another way to write this would be like, this is really the formula for s of xu dot xu hat times xu hat, but each xu hat, each unit vector in the xu direction gives me a length of xu, so in total that gives me length squared of xu. Similar comment over here. Of course then, these are things that we have given lovely names to, like L, M, E, and G. Hey, what do you know? That's exactly the formula. All right, and the same thing goes for x, s of xv. And that gives you this lovely formula here. And then part B of number 8 claims that, if the patch is principal, well, it defines principal. A patch is principal if f is equal to 0 and m is equal to 0. All right, so m was, LMN, m is the middle one. M was the one that had to do with u of uv. So that being gone is really nice, because you look at these formulas here, what happens when m is 0? Gone, right? And you're just left with this term and that term, which goes to show you that s of xu is equal to L over exu. Well, that means that that means that the partial velocity in the u direction is an eigenvector of the shape operator with eigenvalue L over e. Likewise, x sub v is an eigenvector of the shape operator with eigenvalue n over g in the case that m is 0 for part B, the principal patch. And that goes to show you that, in fact, yes, xu and xv are principal vectors, and the eigenvalues, in fact, are L over e and n over g. Hey, while we're at it, one fun thing to notice is that for a principal patch, the formulas for the Gaussian curvature and formulas for the Gaussian curvature and the mean curvature are particularly simple. They're just ln over eg and L over e plus n over g times a half. Very nice, very nice. So obviously you'd like to find principal patches when you can, right? So we'll be like, well, how do you choose a patch which is principal? I don't know. How do you parameterize a curve, right? That's an easy question to ask. It's a much harder question to answer. I'm not sure it can be answered in general. I think that parameterizing surfaces, parameterizing curves, all of these things, it's less of a procedure, it's more of an art. And the more you know, the better you get at it. But it is an art, and some people are artists and some people aren't. But we can all try to paint better. Anyway, so suppose z is non-vanishing normal vector field. So this is section 5.5, the implicit case. And so here O'Neill shares with us this rather conniving method to calculate the shape operator based on a given normal vector field, not necessarily of unit length. So let's go through this here. So you have a non-vanishing normal vector field. For example, like a gradient is a good example, right? Take the gradient, that would be a normal vector field to a surface defined by, like a level surface, g equal to 0. And then, so we want to derive formulas for the shape operator and the, for the curvature and Gaussian curvature, mean curvature ultimately, based on this z. So first of all, it's like, okay, so the unit normal, you can normalize z to get the unit normal, we know that. Because we're trying to derive, we already know how to do things with the unit normal, so we got to go back to that and our definitions and connect it to this newfangled z thing. So the covariant derivative of a function times a vector is, of course, this product rule. And this, of course, is a normal piece, right? And this part, well, this part's also normal. I mean, this we have proved is tangent, right? So if this is normal, this has also got a normal piece in it, right? But they've got to cancel. Just saying. But anyway, so the shape operator, though, because it's minus, shape operator is minus this, right? So it's minus this lovely stuff. Ooh, I seem to have forgot my minus there. Oh, man. Well, this is just very disappointing. Come on. All right. Anyway, moving along. So, of course, we have these lovely formulas for the cross products of the shape operator. Two vectors and the sum of the, the sum of cross products over here. that connects to the Gaussian curvature and the mean curvature in this way. So all you got to do is just basically plug this formula into these two guys, and that will give us formulas. But it'll give us a formula with a v cross w, so you take the dot product with v cross w to get rid of that. We just need two, well, not just any two v and w, we want to pick v and w that give us back z again to connect with the z. So we choose a v and w such that v cross w gives you z. Having done that, we use this formula, right? So k v cross w dot v dot w is equal to that dot that, but s of v is this lovely stuff. S of w is this lovely stuff. But if you think about it, z cross whatever, right, gives me stuff that is perpendicular to the z direction. So when I take dot product with z, that stuff vanishes. Likewise, this cross product with this stuff gives me a vector which is perpendicular to z. When I take dot product with z, that vanishes. So the only thing here that can possibly give a non-trivial bit is basically this guy crossed with that guy. That can have a component which is in the z direction. The normal component, actually. And so that simplifies to just this. I'm just using FV and FW for this thing, all right? But anyway, excuse me. So out pops this, and then, but I said take the dot product with V cross W, which is Z, right? And so, well, there it is. Then you just solve for K, right? K is equal to the covariant derivative of z in the v direction crossed with the covariant derivative of z in the w direction, dot product with the z, all divided by the fourth power of the length of z. What an amazing formula. All right, great. Moving along. So what about the mean curvature? Well, a very similar calculation to the one I just showed you. Gives you this formula for the mean curvature. Again, just plugging in, doing, again, it's based on this formula we had before, and a very similar calculation to this. Out pops that guy. All right, so there's a formula for the mean curvature in terms of the cross product. So this is the z, v and w. Again, we have to pick v and w such that v cross w is equal to z on m. But the funny thing is, when he actually goes to the example, he doesn't really, he finds a z, great, but he never really fleshes out the v and w, which is kind of funny. So I guess that gives me hope for the method, because actually picking a specific v and w such that v cross w equals to z, if you really had to do that in order to use this calculational method, like flesh it out, that would be that'd be a pain. So it's nice that apparently you can find a way around it. Here's how. So look at the ellipsoid. 1/2 the gradient gives you this lovely vector field. X over a squared, y over b squared, z over c squared, the x, y, z components of the vector field respective. And then, so you calculate the covariant derivative in the v direction, which basically just means v eats the x component, v eats the y component, v eats the z component, and then u1, u2, u3. This is the Cartesian coordinate formula for the covariant derivative. All right, so these derivatives are easy to calculate, because that just gives me like the x component of v divided by a squared, y component, what I haven't written is just this. So like v, for example, v of x over a squared is 1 over a squared v of x, but v of x is nothing more than the x component of v. So that's like v1 over a squared. All right, so that's explaining how you get from, well, let's see here, explains this equality. Same thing goes for the y and z. Of course, you can do the same thing for w, right? So you get the same formula except with w sub I over that squared. And then calculating the Gaussian curvature, I need to take the dot product of z with this guy and that guy, right? And so that's a triple product, so I can use a determinant. But hey, it's a determinant, so I can use multilinearity. I can pull out 1 over a squared, for the first column, 1 over b squared from the second column, 1 over c squared from the third column, and I get 1 over a squared, b squared, c squared. And then I get the determinant of this guy. But that, of course, is a triple product. That is the vector x, y, z, which we call big X, which is not the patch. What patch? You're like, wait, what patch? We're talking about a patch. That's right, that's the thing. We never did talk about a patch here. We just talked about the level surface and this this lovely vector field 1/2 the gradient, z, right? That's why this is useful, because we don't have to provide a patch. Anyway, this of course is x dot v cross w, all right? And but v cross w is z, right? So put it all together, you got this over z to the 4th, but this is, well, it's x dot v cross w, right? But, excuse me, z, this is z, right? And z is, excuse me, z is this thing. So if I take the dot product of this with x, y, z, it gives me x squared, y squared, z squared, you know, over a squared, b squared, c squared. So x squared over a squared plus y squared, b squared plus z squared, c squared. And then divided by a squared, b squared, c squared, and then the length is z to the 4th. But that's very nice because we're what? We're on an ellipsoid. So x squared plus y squared, x over a squared plus y squared, b squared plus z squared, c squared equals to 1. So that collapses down to 1, and you just got this. But of course, the length of z to the 4th can be written explicitly as well. And there you go. That's the formula for the curvature of an ellipsoid at the point x, y, z. It's 1 over a squared, b squared, c squared times the square of x squared over a to the 4th plus y squared over b to the 4th plus z squared over c to the 4th squared. Oh, wow. So it's complicated, but, you know, it wasn't actually that much work to calculate it. Again, the weird thing is we never found the v or the w. We just supposed that it was possible to do such, which seems geometrically reasonable, right? If you think about an ellipsoid, if you pick v this way, certainly there's a w you can pick the other way. And if you just, you know, anyway. But saying that and proving it seem like two separate things, whatever. Sphere, of course, is a nice subcase of this example. So if I say a equals b equals c equals r, that gives me r to the 6th here. And this ends up giving me r squared over r to the 4th, which of course is 1 over r squared. So I get r to the 6th times 1 over r squared squared, so that's like r to the 6th over r to the 4th, which just gives me 1 over r squared. The Gaussian curvature of the sphere is 1 over r squared. Hey. So there's an explicit calculation of that, although we gave a fairly rigorous argument for it before, perhaps geometric, but... Now, finally, I would just say, as long as we're on the topic of formulas, right, as long as we're on top of talking about formulas for Gaussian curvature, my goodness, I think that this formula, man, I tell you, if you just want a formula, this thing is a beast. I used this to solve some problem recently, and it was very fun. Now, I don't understand why this is true just yet, but I think maybe we can prove it. So I'm looking for a way to prove that this is true. And this is the 4-dimensional gradient. Oh, excuse me, 3-dimensional. Duh. The 3-dimensional gradient of this level function. So if you have a surface defined by a level function, you can calculate this particular formula, which basically this upper block is the Hessian matrix. You see those second derivatives, right, in the natural order. And then this is the gradient vector, and this is the gradient vector again down here. If you understand this, you can understand where like bunches of homework problems are coming from this thing. This is, I tell you, to understand this would be nice. But, you know, again, I would like to get back to the problem of geometry and, you know, more describing the geometry as best as we can. And so that's what the next lecture is about, special curves. In particular, we'll talk about the 3 special kinds of curves there are: principal, asymptotic, and geodesics. All of those are very important to the story of what surfaces look like. But anyway, of course, this is a necessary, I would say necessary evil, except I don't think it's evil. I think this stuff is really fun. Anyway, thanks. That's it.